The Midas platform demonstrates advanced planning tools, user interfaces, and sensor technologies in an Army context. It includes multimodal interaction technologies from Rockwell Science Center's Integrated Displays Testbed version 3, decision aids from Charles River Analytics Focal Point, and sensors from Rockwell Science Center's Cat's Eye program. Focal Point is an integrated suite of decision aids for the commander and staff, developed in industry and academia and integrated by Charles River Analytics. The suite assists planners in rapid course of action generation, wargaming, elaboration, and visualization. The core of Charles River Analytics' Focal Point suite is the Battlefield Viewer, or BFV. BFV allows the commander's staff to enter information about a tactical scenario on an electronic map display. Information about avenues of approach, lines of defensible terrain, and objectives can be entered using a keyboard and mouse or digitizing tablet with embedded LCD display. Integration with Rockwell Science Center's automatic speech recognition server enables the use of speech in preparing scenario maps as well.
Add AA. Add LDT.
The commander's staff can also enter information about units on the scenario map, including affiliation, type, echelon, strength, location, and task organization. Speech and digitizing tablet stylus inputs can be combined into a bimodal, point-and-speak user interface, allowing the user to point at a specific location on the map and place a unit symbol through speech.
Add armor.
Having populated the scenario map, the commander's staff can then pass the information to the FoxGA wargaming engine using either speech,
Generate plans,
or graphical user interface. FoxGA rapidly generates numerous friendly courses of action and then wargames them against several enemy courses of action using detailed attrition models in the Alternative Courses of Action display developed by North Carolina A&T. FoxGA uses genetic algorithms to repeatedly select and variegate the best courses of action and ultimately returns them to the Battlefield Viewer for playback of course of action simulations.
Play.
The commander's staff can perform further rigorous stochastic analysis on friendly courses of action using the OWL tool developed by Rockwell Collins. Finally, the Cadet tool developed by BBN Technologies helps the commander's staff to rapidly derive a synchronization matrix from the selected course of action. The Rockwell Integrated Displays Testbed version 3 integrates a suite of user interface and sensor control technologies, including wireless PDA interaction, augmented reality, noise-robust speech recognition, electronic display stabilization, look and speak interaction, point and speak interaction, live information from wireless sensor networks, 3D audio spatialization, 3D terrain visualization, and wireless multimedia information systems. These technologies allow access to information across a range of platforms, from the pocket-sized computer for highly mobile users, through mobile vehicle systems, up to the stationary command center. The wireless handheld PC and wireless PDA are lightweight information systems for highly mobile users with a low tolerance for encumbrance, such as the commander. On the display of the handheld PC is a small overall scenario map display called a mini-map, which shows the known positions of friendly blue and enemy red units. Mobile users can remotely monitor planning activities in progress or a tactical situation map during operations using touchscreen interaction with the Minimap application. Planning data, such as course of action simulations developed in the Charles River Analytics Battlefield Viewer, can be downloaded through a wireless internet connection and reviewed on the PDA. Different friendly and enemy courses of action can be selected using drop-down menus. Speech recognition and graphical transport controls allow the user to play back the planned simulation and restart and review the simulations as necessary. Detailed information about a particular unit can be obtained by tapping the stylus on the screen on or near the unit icon. Upon returning to the Tactical Operations Center, the commander can dynamically synchronize the wireless PDA with the larger, more powerful information system. Using a stylus and touchscreen, different regions of interest can be selected on the minimap display. At the same time, the selected region of interest is shown in greater detail on the large display. Using a wireless microphone and remotely located speech recognition server, the user can also ask questions of the system, such as casualty list. The system responses to speech queries are shown in a text window overlaid on the minimap display. Effectiveness report. While on the move, the user can still enjoy a limited amount of interaction using only the wireless handheld PC or PDA. By pressing a graphical button, a point-and-click mode of operation can be engaged to direct the movement of friendly forces. A named unit, such as Company Alpha, can be selected by pressing on its respective graphical button. Having selected the recipient of the command, the user can then tap on a specific location on the minimap display to order that unit to move there. The progress of the unit is shown concurrently on both the minimap display as well as the large display. By pressing on the appropriate graphical button, the speech recognition and stylus input methods can be combined into a bimodal point-and-speak user interface on the wireless PDA. In this mode, the user can directly point at a specific location on the map and then use speech to indicate how that pointing input should be interpreted. Move Company Charlie here. In response to the point-and-speak input, Company Charlie moves to the designated coordinates. Augmented reality is a technique for naturally and intuitively displaying information about the user's environment in the correct spatial location overlaid on the user's field of view. A translucent, head-worn display allows the user to see the real environment beyond a computer-generated graphical overlay. The principal challenge in augmented reality is the correct registration or alignment of the computer-generated graphics with the scene on which they are superimposed. This, in turn, requires that the position and orientation of the user's head must be determined and tracked. For alignment of augmented reality displays on surrounding terrain, the user's position can be obtained with sufficient precision using a global positioning system receiver. The approximate orientation of the user's head can be obtained using a combination of head-worn sensors, including a digital compass to provide yaw information, an inclinometer to provide pitch and roll information, and a gyro to provide rapid updates of head orientation during fast motion. In this example, terrain profile information is rendered onto the user's display to indicate the presence of hills and mountains, which are currently obscured by fog. When visible, the horizon silhouette itself can be used for higher precision registration of graphics in augmented reality displays. A miniature camera affixed to the head-mounted display is used to digitize the horizon silhouette. Edge detection algorithms help to identify the profile of the horizon. Features such as mountain peaks and valleys are detected by the system and compared to a digital terrain elevation database to determine the precise orientation of the user's view. Information about known locations or objects in the user's vicinity can then be accurately shown in place on the user's view. Augmented reality displays can be presented in real time either on head-worn displays or handheld displays with video capture capability. In urban environments, the reliability of global positioning system signals and magnetic compasses is reduced. A visual tracking technology has been designed by Rockwell to provide position and orientation information for precise overlay registration in augmented reality displays based on visible features of buildings. An overlay of the wireframe model of a building onto the captured video image provides the framework to visualize any available additional spatial information about the exterior, interior, or occupants of the building during urban operations. In order to use speech reliably in military environments, the noise robustness of traditional speech recognition technologies must be improved. An inline noise reduction filter has been developed for improving the performance of existing speech recognizers in the presence of both stationary and moderate non-stationary noise. In a relatively quiet environment, a commercially available, off-the-shelf speech recognizer, such as IBM's ViaVoice, encapsulated in Rockwell's ASR server technology, can recognize speech with reasonable performance.
Move company alpha here.
In response to the speech input, the recognized words are shown on the screen. In the presence of severe ambient noise, such as the non-stationary noise source heard here, the speech recognizer is unable to correctly recognize the user's speech.
Move company alpha here.
By activating an inline noise reduction filter, noise is removed from the speech signal, allowing the speech recognizer to operate successfully.
Move company alpha here.
Another innovation for improving speech recognition performance in noisy environments is the physiological sensor, developed by Army Research Labs. This body-coupled transducer operates on a principle similar to a conventional microphone, except that it is coupled directly to the user's body, thereby providing significant noise rejection. In addition, the physiological sensor can be used to monitor the wearer's vital signs, such as heart rate and blood pressure. The physiological sensor has been integrated with a bimodal speech recognition server developed by Rockwell, enabling the user to interact with the Minimap application either on a wireless handheld PC or on a mobile desktop computer.
Effectiveness report. Casualty list.
The Rockwell bimodal automatic speech recognition server combines both visual and acoustic modes of input to recognize speech. The lightweight head-worn apparatus shown here consists of a typical head-worn microphone combined with a small CCD camera which views the user's lips through a mirror. The image of the user's lips is digitized and analyzed in real time. Fast lip detection and tracking algorithms developed by Rockwell enable automatic extraction of relevant geometric and pixel-based visual features to assist in word discrimination. By combining these features with traditional acoustic speech features, the resulting recognizer is capable of more robust performance in noisy environments than a recognizer using acoustic features alone.
Move Unit 7 to Charlie 5. Move Unit 3 to Delta 6. Move Unit 3 to Delta 4.
For limited vocabularies, the user can also dynamically switch to a purely visual mode of speech recognition. By recognizing speech in a purely visual domain, the system becomes immune to acoustic noises, even severe impulsive noises such as gunfire or explosions. Visual speech recognition is also useful in situations where stealth is required. The user can simply mouth his commands without actually speaking, and the system will still recognize his speech with the same amount of accuracy. In addition to acoustic noise, users in a C2V or other mobile environment are subject to significant vibration and other motion while on the go. Using an accelerometer, this flat panel display is electronically stabilized in one axis. As the screen is perturbed, simulating the motion of a vehicle, the application window is moved to compensate, enhancing the readability of text. When the vehicle comes to a rest, the application window gradually returns to its normal position. A head-worn linear accelerometer can be used to compensate for the motion of the user inside the vehicle relative to the display, both vertically and laterally. Using the same protocol as the wireless PDA, this isometric map display can download course of action simulations from the Charles River Analytics Battlefield Viewer decision aid for more detailed review. The isometric map display depicts constituent units one echelon below those units depicted in the Battlefield Viewer. Using a stylus and digitizing tablet with embedded LCD display, the user can select individual units. Using a rubber band type selection, multiple units can also be selected at once. In a visually cluttered field such as the one shown here, many units might be selected by such a simple spatial gesture. The selection can then be refined using speech commands.
Select armor in this region.
The user can also point at any location on the map and issue speech commands to specified or selected units.
Move here.
Units on the isometric map display can be represented using either traditional military symbology or animated icons. The Unmanned Aerial Vehicle, or UAV, unit can be used to scout for enemy forces.
Move here.
As the UAV traverses the terrain, previously unknown red forces are uncovered and shown both on the primary display as well as the minimap displays of mobile users. Having discovered the locations of enemy forces, the user can verbally select a named unit
Locate Company Bravo.
and then point at any enemy unit and order an attack.
Attack this unit.
As the blue and red forces engage in simulated combat, sound effects are played. As the display is panned left and right, the sound effects are spatialized accordingly to help cue the user as to where events are occurring. Users in a stationary environment can exploit capabilities such as eye and head tracking shown here. This ball cap includes an infrared source and camera, which are used to track the direction of the user's gaze. A scene camera embedded in the cap shows the scene visible to the user's eye. This head tracking apparatus uses ultrasonic triangulation to track the position and orientation of the user's head in 6 degrees of freedom. Information about the user's direction of gaze and the position and orientation of his head are combined with knowledge of the locations of displays in his vicinity to enable a gaze-based interface. In this example, the user can concurrently monitor 3 different media streams on flat panel displays. As the user looks from one display to another, a red outline is drawn around the display he is gazing at. Audio from the gaze-designated media stream is also emphasized.
Now we are united in resisting.
That's causing the snow tonight in western.
Toward the tension in the region, Israel threw a...
Using a microphone and speech recognizer, the user can also look at any particular display and issue speech commands.
Pause.
In response to the user's command, the media stream is stopped. The user can also scan through the media content by speech
Seek plus 60.
causing the media content to advance by 60 seconds.
Continue.
The user can also look at any media display and ask for any available media stream to be shown on that display.
Show surveillance.
Tomorrow.
Show weather.
Slides through. It's already through Atlanta.
The user's gaze can also be tracked across sectors of a large format display, such as the isometric map display shown here. By pressing a key or issuing a speech command,
View contours.
the map coordinates of the sector at which the user is looking can be passed to this 2D contour map display.
View contours.
The display shown here is a two-dimensional isometric map, which is easy to navigate through while still providing the user with an impression of depth and elevation information. At times, the commander may wish to see the lay of the land from specific vantage points, or to check for the effects of limited visibility. The coordinates of a specific viewpoint, such as the one marked by this tower icon, can be sent to a 3D visualization system, as shown here. In this 3D rendering mode, the same terrain data are depicted in 3D perspective. Objects which populate the 2D isometric display, including avenues of approach and lines of defensible terrain, are also shown in 3D in this display. As in the isometric map display, units are shown using either traditional military symbology or 3D models.